As we go through this lecture, here is a question that I'd like you to think about. Let's say that we have an RGB image of 784 pixels. Does it make sense? Is it ideal or optimal to represent this as a tensor which shape 784, 3? Is this an optimal representation of the pixels in an image that is represented in RGB format? Now that we've understood the one hot notation for representing the labels of these MNIST images, let's also understand the feature vectors that we are going to go with. There are different possible ways of expressing an image using a feature vector. We will go with a representation based on the 784 pixels which comprise each image. And do recall that each image is a grayscale image, 28 pixels in height and width, so 784 pixels in total. Each one of those pixels is a grayscale value, which means that it is represented using a single channel. That channel is going to correspond to a number between 0 and 1. 1 represents white and 0 represents black. All of the numbers in between represent shades of gray. With this representation, let's take a look at how we will create a feature vector corresponding to one image. In effect, we are going to make use of a 784 element vector. We will do so by flattening all of the pixels in an image and adding them or tacking them onto one single long vector. So our feature vector is going to consist of a tensor with just one dimension. That tensor is going to have a shape of 784. Now, you should be aware that this particular representation of an image is actually a lossy one. It's not the best representation. This is not the representation which we would use with a more advanced technique such as a convolutional neural network. Convolutional neural networks represent the state of the art in image recognition problems like this one, and they work with feature vectors that are grids. Here we are not using a grid, rather we are using a single long vector with just one dimension. A grid is a better representation because it captures information about the artifacts of the image. It, for instance, will take into account that pixels which are at the edges or the boundaries are grouped together in a specific way. That information is lost in this flat representation. To see how, consider that the first 28 elements in our 784 element vector correspond to the first row. But now when we switch to the second row, or all of the rows in between, we are losing the fact that those rows are stacked together. We are losing the fact that some of those pixels are very close together when represented in a two-dimensional format, but very far away from each other when represented in a flattened one-dimensional format. In any case, this flattened one-dimensional tensor format is easy to use for our purposes here. If we were going to use a more advanced algorithm and if we wanted a high level of accuracy, we would have gone with a two-dimensional representation rather than this flattened one-dimensional one instead. The next step in our algorithm is going to involve calculating the L1 distance between a test digit and all of the training digits. Doing this requires jumping through a few hoops in TensorFlow, so let's understand exactly how we accomplish this. Let's say we have a single training digit. This is a 784 element vector, so it has just one dimension with 784 elements. We want to calculate the L1 distance of this training digit from a test digit, which is also a 784 element vector. So what we are going to do is to first compute the negative of the test digit. We do so using the function tf.negative. This is a standard TensorFlow function. Once that's done, we add up the two vectors. This has the effect of calculating an element-wise sum of the two vectors. Because one of these is the negation of the test digit, in effect what we've done is to perform an element-wise subtraction of the test digit from the training digit. Notice again that this element-wise subtraction is because we negated the test digit using tf.negative, but we did not negate the training digit. That is exactly as it was in our dataset. We will now go ahead and repeat this set of steps for every image in our training data. The MNIST data comes in batches of 5,000 training images at a time. So we will go ahead and calculate 5,000 vectors, each of which correspond to the element-wise difference between the one test digit and each of the corresponding 5,000 training images. So at the end of this process, we are going to be left with 5,000 vectors, each of them with 784 elements each. Now, while calculating the L1 distance, we really focused on the absolute value, that is the number of steps that we need to take in order to go from one vector to the other. So we've got to apply the TensorFlow tf.abs method to convert any negative values into positive values, because after all, we are going to add all of the distances irrespective of their sign. So go ahead and invoke the tf.abs method on each of the difference vectors which we obtained by comparing our one test digit to each of the 5,000 training digits. The values highlighted in orange are the ones which flipped sign, they were negative, but while calculating the L1 distance, because we need to focus on the absolute values, we consider them as positive instead. Next, we will go ahead and add element-wise each of these vectors and reduce them into just one number per distance vector. We do so using the tf.reduceSum method, which simply adds all of the elements in a vector. So for instance, the value 1 is equal to the sum of all of the elements in the absolute vector, which was previously calculated. So where we previously had 5,000 vectors, each with 784 elements, after applying tf.reduceSum to each of these, we are going to be left with 5,000 vectors, each with just one element. Each element corresponds to the distance between that training digit and the test digit. Because there are 5,000 training digits, we are going to end up with 5,000 distances. The next step for us is to sort all of these distances and then take into account some kind of average of the k neighbors which are nearest to our test digit. Now, the simplest case of the k nearest neighbors algorithm is where we just consider the one nearest neighbor. In that case, we don't even really need to sort. All that we need to do is to find that value which has the smallest distance that would correspond to the digit which is closest to our test digit in the training data. So let's take stock of where we stand. We've calculated the L1 distance between each training digit, between each of the 5,000 training digits and the one test digit. Now, all that's left for us to do is to actually run the algorithm and take into account the k nearest neighbors to find what this test digit is. In general, for values of k greater than 1, we will need to sort by distance, by L1 distance, find the k nearest neighbors and perform some kind of average or election algorithm within those k nearest neighbors. But if we use just k equal to 1, all we need to do is to find the one image in our training data which is nearest to our test data. This can be accomplished in TensorFlow with just one command. It's called np.argmin. np.argmin is enough to find the index of the nearest image in our training dataset. We can then figure out the label corresponding to this nearest neighbor and use that as our assessment of the test digit. Let's now turn back to the question that we had posed at the start of this class. Let's say we have an RGB image with 784 pixels. It is not optimal. It is not really the most efficient way to represent this tensor as of shape 784, 3. The second element, that the 3 represents the number of channels. That is fine because that is indeed the number of channels in an RGB network. But the first element of the shape vector, which is 784, indicates that we have represented all of the pixels as one long unidimensional array. That causes information to be lost. For instance, information about which pixels are adjacent to each other when stacked vertically. While using convolutional neural networks, which are the most popular type of neural network for working with images, we would typically not use one long single array with all of the pixels laid out one after another. We would most likely go with a 28 by 28 array if those are the width and the height of the image respectively.